Hello guys, so welcome back to our lecture 14. We're gonna continue our discussion about peak rectifiers or the diode rectifiers with smoothing capacitor or filter capacitance. So last time we discussed about the peak rectifier without a load, but this is not of course practical. Practically you have some load, you have some resistor like this one, and you want to feed this resistor with a DC voltage or a DC current. Okay, so let's now analyze the circuit and see what will be the differences between the output of this circuit and the output of the previous circuit. Okay, so the output of the previous circuit was just constant. So we said that between 0 and that point, which we call T.7, at which the input will reach 0.7, the diode will be off, so the capacitor will not charge or discharge and will keep its voltage, which is 0. So initially VC is equal to 0. Then it will start charging and follow that pattern here until it reaches Vmax minus 0.7. Okay. Then after this point, which is T over 4, basically the diode will be off all the time. And the VC will keep its voltage, which is Vmax minus 0.7 forever. This is with if there is no load connected, or if the load is equal to infinity, basically, open circuit, okay? So basically what's gonna happen is that the output will be DC, completely perfect DC like this. And this value is Vmax minus V7, minus 0.7. If the diode is ideal, or if the, for example, if it's not a silicon diode, some other diode that has very small voltage drop, not 0.7, it will be the ideal, model will be very valid in that case. And there is no 0.7, so whenever the switch will become closed, the capacitance will charge until it reaches Vmax, because Vd is equal to 0. No drop on the diode, so it will continue like this with a voltage equal to Vmax. This is basically with the ideal and the constant voltage model. Whatever you choose, of course, this will be given, for example, in the exam or the question, and you should follow what's given or what's required. Now let's see the situation when we have a load, a resistor, which is not infinity, not open circuit. Okay, again, we're gonna assume that at T equal to 0, VC is equal to 0. Okay, then the switch will close. So this will be short circuit like this, and the input will be applied. Again, we have a 0 here, 0 voltage, because VC is equal to 0 at T equal to 0. So the out is also 0. So the N side of the diode has a 0 voltage. So, and the B is just equal to V input. So if V input is less than 0.7, the diode will be off. So when V input is less than 0.7, the diode will be off. So no charging. Then when the input exceeds 0.7, for example, at 0.7, this point will have a 0.7 volts. This is 0. So VD equal to 0.7. So it will start on in the transition point. So when V input with VD is equal to 0.7, so the diode will be on. So there will be a current. IC is greater than 0. This is IC or ID. Both are equal. And the capacitor will charge. So the capacitor will start charging. And it will develop a charges here, positive charge on that plate, negative charge on that plate, because this is the charging current. And this will continue until the voltage reaches the input voltage here reaches Vmax at that point, or that point, let's go with the constant voltage model. So we're gonna, follow this. So this is the point in which the the input reaches Vmax. So at that time, Vc will be Vmax minus 0.7. So at t equal to t over 4, Vc will be Vmax minus 0.7. Then the input will drop than Vmax. I mean, the input will now start to decrease than Vmax. Okay. So we proved last time that the diode will be off. So the capacitor will not charge again. Okay. So how about, so after t equal to t over 4, or we can say at t larger than or greater than t over 4, no charging, because the diode is off. But this time, this will be to certain time. I mean, it will not be forever off. We're gonna see that after some time it will become on again. So no charging. But how about discharging? So let's now check the discharging situation. And if there is no load, so if the discharging will have a current, in that direction. So this is I discharging this. If there is no load, this current has no way except the diode, but the diode cannot permit currents flowing from N to B. So this current will not flow through the diode. This was in the previous circuit when we don't have, a load. But now there is another way, which is through the load here, so the resistance. So there will be this charging through that resistance. Okay. So there will be discharging. So after t over 4, or at t greater than t over 4, the capacitor will discharge through the resistance. If the capacitor will start discharge, that means it will lose some of its charge. So Q, the charge of the capacitor, will decrease. Basically, this is charging. And since VC, the voltage of the capacitor, is equal to Q, the charge of the capacitor, over the capacitance, which is constant, since Q is decreasing, VC will decreasing. So VC will decrease as well. And that's not good. Yes, that's really not good. Because when we don't have a load, the load is infinity, the voltage become constant, just DC. But now no, it will decrease. So let's study the this decay in voltage, or this decrease in voltage, and its relation to time and the capacitance and the load resistance. And let's see if we can control it somehow so it will not decrease so much. So in this charging, Vc of t while discharging has equations that relates this voltage to the time, the resistance, the capacitance, and the voltage from which it starts discharging. And this is basically V initial, or V, let's call it V0, or V initial exponential minus t, the time, over RC. So let's draw this. If we want to draw this relation here, if this is the time, and this is Vc of t while discharging, at t equal to 0, so Vc of 0 will be equal to Vi times e to the power of 0. E to the power of 0 is just 1, so this will be Vi, V initial. Then afterwards, the exponent of the exponential will be not 0, and it has a value, negative value, so it will be less than 1. So basically, it will be something like this. Good. Now, can we control such decay? I mean, can we increase or decrease the rate of decay? How much the voltage is reduced per second, for example? And the answer is yes. So let's call this RC tau. Tau equal to RC. We're gonna call it tau for some, for some time. So let's call this tau 1, for example, or tau. So the original value RC is equal to tau. Okay. If we increase R or C such that tau will increase, this will be the decay. Tau 1 and tau 1 is greater than tau. If we decrease R or C or both, okay, so tau will be decreased. So this will be the rate of reduction, tau 2, and tau 2 is less than tau. So basically, if you have greater RC, greater tau, okay, this will make the decay slow. So if we increase R or C or both, tau will increase. If tau increases, the decay slows down or slow down, which is good. For example, if the extreme case, if RC equal to infinity, and that's basically easy to do, by the way, I will tell you in a moment. If RC is equal to, which means tau is equal to infinity, this will be the shape of Vc of t. It will be like this. Constant equal to Vi. And why is this? Basically because e to the power. So this is basically why, because e to the power of minus t over infinity equal to e to the power minus 0, which is just 1. So Vi times 1 is just Vi. Good. And that will be basically, this is DC. So in our application now, we have a load, and of course you can't control the load. This is your, for example, your phone. So your phone, you bought it, you don't have any control over this phone. So the charging circuit inside the phone has some input resistance that you can't control, but you are now designing the rectifier, the charger. Okay. So when you or the adapter that converted from AC to DC to charge the battery of the phone. So this is your design, the adapter, the charger that converted from AC to DC. So you can control the value of the capacitance inside this charger so that the decay will be very small. The problem is, if you increase the capacitance, you increase its area, the size of the capacitance will increase. And maybe also the cost. So it's not free, But if you need, you can. Okay. So basically, we need here big RC. So the requirement here to get slow decay or slow discharge is to increase the capacitance C. Why? Because we usually don't have control over the resistor or R. Good. So, how much is this increase? Okay. So you have here an input. This input has some, is also related to time, a function of time. Okay. So this increasing of tau is also controlled. I mean, it will not be infinity. How much capacitance we put, we can control that also. We can choose that also. So a good choice here is to make RC, good choice, to choose RC much greater than T, which is the period of the input voltage, V input. Okay, that's basically, for example, 10 times. Usually you can when you have this much greater than, usually designers consider it 10 times or something. Good. So let's now apply what we discovered now on our output here. So I'm gonna remove the previous outputs just to not to confuse us. I'm gonna draw now what we get from our circuit, our new circuit. So our new circuit will not work. I mean, the capacitor will not work until we reach 0.7. Here is the input reaches 0.7 at that point. So it will charge like this until it reach Vmax minus 0.7. Then it will discharge through the resistance here. Okay? If RC is small, it may discharge like this. Then becomes 0. Then it charge again. And then discharge. And so on. If we increase a little bit tau, it may become like this. Then become 0. Then it charge again. Then discharge. Increase a little bit more, it can become like this. As we increase tau or RC, the rate of the reduction or the decay or the discharge becomes slower. Then it charge again. Okay. Usually you have something like this. Let's do it with red. Then a little bit of a charge. Then reduce again. So let's now quantify these values. This distance in time, remember, this is t over 4, and this is t plus t over 4. So this distance is just t. Okay? This distance, let's call it t dash. And clear here, t dash is less than t. That's of course. Okay? So we usually, when we choose RC much greater than t, usually we get, if we do that, t dash much closer to t or approximately equal to t. I mean, the difference here, this difference is very small. Delta t is delta t, let's call it delta t, which is t minus t dash, is very small, approximately 0. Good. So our final output, I will draw it again on the input now, just to avoid the confusion. This is our final output. It's really, we have succeeded to reduce the, the fluctuations that we have in the half-wave rectifier a lot. a lot. Still, there is fluctuations, but remember, first we have constant direction because here the voltage is always positive, okay? And the fluctuations has reduced a lot. Now, the moment to measure these fluctuations, how much we want to quantify our achievement, okay? To quantify this achievement, or to judge if this peak rectifier is good or not, we measure what's called the ripples, which is basically the voltage or the difference between that point and that point. Of course, if this difference, let's call it delta V or VR, V ripple peak to peak basically. If this difference is very small, that means we succeed in reducing the the fluctuation more and more. Actually, if it was zero, if you have here an infinite resistance, okay, open circuit, okay, then you will have something like this. There will be no fluctuations at all. Okay, good. So let's find this variable. So the variable, if we go back here to the, here, if we want to determine variable, let's do this with another color. This guy, for example. So this is variable, the distance or the voltage at that point, which is Vmax minus 0.7, minus the voltage at that point. Let's call it V1, for example. Okay. So variable or VR is equal to Vmax minus 0.7, that point, minus V1, which is that point. Good. We know Vmax minus 0.7, but how about V1? How we can calculate V1? So basically, we can calculate it if we know the relation of that line here, that decay. But we know the relation because Vc of t during this charge equal to Vi. What is Vi? Look at this equation. Here is the equation of the discharge. We need Vi. What is Vi? The voltage at which we start the discharge, which is that voltage, which is also Vmax minus 0.7. E to the power minus t over RC. That's it. But this is a nonlinear, relation, nonlinear function. Can we approximate it? Yes, we can approximate it. And the reason for that, because we choose RC much greater than T capital. Okay, so it is very slow decay. It is something like, let's compare it here. It is something like this, very slow. So this guy, this new curve here, will bend, at a very high time. So it's in the beginning here, it's like linear. So we know that if T is much smaller than RC, E to the power minus T over RC can be approximated as 1 minus T over RC. This is from math, this is from math, that if the exponent of the exponential, but with minus, is very small, very smaller than 1, approximately 0, then we can approximate the function E like this. Okay, so Vc of t, basically Vc of t approximated as Vmax minus 0.7 1 minus t over RC. So let's apply that here. So VR equal to Vmax minus 0.7 minus Vmax minus 0.7 1 minus t over RC. But this is not, this is Vc of t. We want here the voltage V1, which is at that time here. Okay, which is T dash. So V1 is the voltage at T dash. This should be T dash, not just T. But we know that T dash approximately equal to T. So this VR equal to, and we can also distribute this over this parenthesis here. So Vmax minus 0.7 minus Vmax minus 0.7 plus Vmax minus 0.7 T over RC. This will go with this. So finally, Vrip equal to Vmax minus 0.7. And remember, T is the period of the sine wave. So and the period is equal to 1 over F, 1 over the frequency. 1 over FRC. And it's very clear here, guys. If we increase the capacitance or the frequency of the input signal, VR will be reduced. Usually we have only control over the capacitance. We cannot control the resistance, which is the load. And usually we connect directly to the outlet here, the standard outlet, which has fixed frequency of 60 Hertz. So basically, we have control over the capacitance only in our design. So if you increase this capacitance, variable will reduce too much, as you will see in the lab as well, so that we can just consider the output as really good, very good DC. Okay, so that's basically, guys, how to analyze the circuit when you have a load. In the next video, we're gonna do the same, but for the full wave rectifier. Okay, this is, remember, this is the half. So this is basically the half wave rectifier plus a capacitor. The only difference here between this circuit and the half wave rectifier that we studied, the most of the half wave rectifier, is the introduction of the capacitance in parallel to the output. So that's what we'll basically do with the full wave rectifier as well. We just draw the same circuit and just put a capacitance, in the output parallel to the load. Thank you very much, guys, for watching this video, and see you in the next video. Bye-bye.